In my last video, I talked about damage reduction and its mechanics. This video not only serves as a follow-up to clear up some misconceptions, but also talk about the new developments that have been made. Namely, draining stake, the fearmonger skill, and most importantly, the pattern to damage reduction. Oh yes, it was solved, but not by me. A brilliant user named LeBlanc on Discord managed to find the pattern and even wrote code that accurately predicts the depreciation of damage reduction. I'll put his code in the comments and description, and I'll talk about that towards the end because it's really complicated. But firstly, allow me to address some common questions and misunderstandings. I've seen my fair share of people asking what accessories give mitigation or damage reduction and are under the misconception that Cleric Hat gives mitigation. I would like to reiterate that Cleric Hat does not give mitigation, but rather gives damage reduction and flat defense via the expenditure of Cleric Shield stacks. Now, I can see why some people may have confused the two ideas because I kind of formatted my video in terms of complexity and not really cohesion, so I would like to apologize for that. To know if an item gives mitigation or damage reduction, please refer to this table which I spent an unreasonably long time making. Now, we move on to the new discoveries. Let's move on to draining stake first. Now, this accessory is kind of odd. The weakness applied decreases the damage of the enemy by around 20% after consistently applying weakness, and acts directly on the enemy's damage. Therefore, it is neither mitigation or damage reduction. Now, this percentage varies from enemy to enemy, most likely due to status resistances. Now, for example, the club swing of ogres do around 77.68% of their damage, resulting in 27.17 damage being dealt, while Old Fart's Head Slam does around 132.28 damage, which is around 82.6%. Now, since you don't have a very good way of knowing when an enemy has status resistances, I recommend just multiplying the enemy's damage by 80% if you're going to do damage calculations. Then we have Fearmonger, which increases the damage multiplier by an additive amount. Now, since I haven't really gone over how stat scaling works, I recommend watching Highway Suns' video on how to calculate your damage, because he goes over how items work in general, like damage multipliers and such, and he also talks about Fearmonger, which is, related to what I'm talking about right now. I'll put his channel link in the description. Now, Fearmonger also decreases the damage of the enemy by a flat amount. This flat amount is dictated by this formula, which means that if you have base Fearmonger, which means Scary 1, you need to deduct 10% of the original damage from the original damage itself. This decrease acts on the enemy's damage after weakness from draining stake, but before flat defense. Hence, it is also neither mitigation nor damage reduction. Although the way Scary works can be interpreted as multiplying the damage by 90% and 80% respectively, this interpretation is incorrect when we consider the weakness debuff, which I will demonstrate soon. Final thing to note here is that Scary is not affected by Milady Metal whatsoever, so no Scary free, guys! Now allow me to present a quick proof by contradiction on why Scary cannot be multiplicative. Here we have Old Fart, who does a 160 damage head slam. Now consider stake and Fearmonger separately. With only draining stake, he does around 82.6% of his damage as previously mentioned, so just multiply that to 160 to get 132.28. Now with just Fearmonger aced, his damage is reduced by 20% by this formula, and hence he does 128 damage. But if we mix both factors, he does 100.28 damage. Notice that there is a 32 damage difference between when we applied only draining stake and when we applied both Fearmonger and draining stake. Now, notice that 32 is 20% of 160, which is the original damage. Now, this doesn't line up with the calculated value if we simply multiply the damage number of 160 by 82.6% and 80%. Therefore, the damage decrease provided by Scary is a flat amount which is dependent on the original damage of an attack, and applied after weakness. Okay guys, before we get into the explanation of damage reduction, do note that this math is not particularly easy. We will need to introduce 3 new concepts, with the first one being the summation sign, signifying repeated addition till the nth number starting from what I is equal to. You calculus students probably know what this already is. Now the second one is the uppercase pi symbol, representing repeated multiplication. So basically the sigma notation, but with multiplication instead. And finally, the concept of sequences in mathematics. Now, are you ready for the math to get even worse? And finally, to the complete explanation on how damage reduction depreciates. But firstly, let's jog our memory. We concluded that damage reduction depreciates with more sources, and that the depreciation acts on sources of smaller or equal values of damage reduction. For example, using vexation aced and combustion engine of 50% damage reduction and 25% DR respectively, the 25% undergoes depreciation by this formula and is added to the 50% DR of vexation aced. Speaking of which, let's go back to the second order damage reduction formula I wrote in my previous video. Now, I'm going to change the formula such that instead of inputting in integer values, we enter their decimal version instead. So instead of 50, we use 0.5. Hence, the new formula would be this. Factorize it into this form, and we'll multiply the 1 over 5 into the second part of the equation for the sake of readability. Now, let's assume that there are 3 sources of damage reduction, listed in descending order called A, B, and C respectively. With reference to LeBlanc's code, allow me to present the third order damage reduction formula. Look closely, there's a rather interesting pattern. So, tell me, did you notice that the coefficients all build off of the previous terms? Let's take the second coefficient for example. The previous term before it is A, and notice how A is involved in both parts of the factorized form. Now in the third coefficient, notice how in place of the A, the previous equation in its entirety is there, which signifies the resultant damage reduction while the 1 minus 0.4a remains constant, and is then multiplied by 1 minus 0.4b. Therefore, we can infer a pattern, which is that the coefficient of the n plus 1 source of damage reduction is 1 minus the resultant dr up to the nth source times 1 minus 0.4a times 1 minus 0.4b all the way to 1 minus 0.4 times the nth source. Since this is only the coefficient, we need to multiply it by its corresponding damage reduction value and add it to the previous resultant damage reduction, making a new resultant. And this is also how LeBlanc's code works. Remaining refers to this part, where it is defined by itself deducted by the resultant damage reduction. Remaining's value is always set to 1 after calculating the resultant dr. Current dr is a singular source of dr which is to be multiplied by its corresponding coefficient, and multiplier refers to this part where it is itself times 1 minus 0.4 times the previous dr term of the current dr. The remaining, multiplier, and the source is then multiplied together, and the sources are all summed up. Let's use an example. Referring back to the third order damage reduction formula, we can try and fit our variables to the 3 things LeBlanc defined. As you can see, we have 3 sources of damage reduction named A, B, and C respectively. We have to treat dr as separate sources starting from top to bottom. As such, let us start with A first, which will be the current dr. Consider the remaining component. It is defined as itself minus previous resultant damage reduction. Since the previous resultant is 0, that means remaining is 1, and now let's consider the multiplier, where it is defined as itself times 1 minus 0.4 times the previous dr term of current dr. Now the previous dr term is also 0, so it is also 1. Hence the coefficient of a is this, which means it is also 1. Now, since the coefficient of a has been calculated, the current damage reduction shifts from a to b. Consider the remaining component of b now, as it is defined as remaining deducted by previous resultant damage reduction. With the previous resultant being a, and remaining being set to 1 again, we need to deduct a from 1. Now consider the multiplier, which is multiplier times 1 minus 0.4 times previous dr term of current dr. As the previous dr term is a, we just plug it into the equation, and we get 1 minus 0.4a. Multiply everything to get this, which lines up with my original formula. Now, since the coefficient of b has been calculated, the current dr shifts from b to c. Repeat these steps for c. Remaining is now this, the multiplier is this, and the current dr is c, so multiply everything together and we get this expression. Hence, the depreciation of damage reduction cannot be represented by one simple formula, but rather an infinite series where its coefficients build upon previous iterations of itself, exhibiting signs of recursion. The most accurate way to think of this is as a function with infinite inputs. But could you derive the pattern? Well, it's entirely possible if exact values are obtained, because that's exactly what I did, using a ton of regression. But with the rounding system of Pilgrammed, it's pretty much impossible to do so, and never would I ever expect an infinite series. Had LeBlanc not been able to guess the pattern correctly, I don't think I would have ever cracked the code, so major thanks to LeBlanc for making this possible. Now, I'd also like to thank Char, please, because he helped explain the code. Guys, I don't take computer science. I don't know how to read this. This is unreadable to me. So, yeah. Though, I must mention that you'll be seeing this guy a lot in my next video.